Hello children, welcome back to the channel. Today we will be continuing our discussion of angular momentum. We have already discussed or found an expression for angular momentum, the vector expression for angular momentum. We have also understood what it physically signifies, and we also found a relationship between the torque and angular momentum. In continuation of our discussion, today we will be taking up, try to understand what it means geometrically. That is geometrical interpretation of angular momentum. Now let us consider we have a particle at point P which is moving under certain force and moving with certain velocity, right? And let's say its initial position vector is given by, it was at point P and its position vector was given by vector r. Now after some time, say small amount of time delta t, it has moved a little bit and it leads to a new position q whose position vector is given by r plus delta r. Okay, so the displacement of the particle is from P to Q, right? So PQ will give us the displacement vector, and PQ will be simply, if it is the origin, OQ minus OP, or we have OQ is R plus delta R minus R, that is to say PQ equal to vector delta R. Okay, that is the displacement vector. Now we have said that it has taken around a time of delta t to reach from P to Q. So if V was the velocity, which we can consider constant for the small elemental displacement, we can say delta R can be written as the velocity multiplied by delta t. Clear till now? Okay. Now let's consider the geometry of the problem. We can always expect, or we have already in our discussion of cross product, we have seen that we can do what, draw a line parallel to the vector delta r, and if I connect these 2 points, say let's just call this point r, then OPQR, the parallelogram that is formed by vector r and at one end and vector delta r at another end, right? If we form this vector parallelogram, then we know that the area of the parallelogram formed by the two vectors is given by the cross product of the vectors, that is vector r and vector delta r, that is r cross delta r will give us the area vector of the parallelogram that is formed. And what will be the direction? It is r cross delta r, so r from vector r to delta r, this is the delta r vector. So if I take the right hand screw rule, it will be up, that means it will be along positive z axis. So the cross product will be along this, right? Since the two vectors are lying on the xy plane, so their cross product will be either along the positive z direction or along the negative z direction. Since we are taking r cross delta r, so it will be along positive z direction. Okay. Now this result was found in our discussion of vector cross product. If you haven't seen my video on vector cross product, the link will be given in the description below. You can refer to that. Now, if the area of the parallelogram PQ OPQR is this, then we also found that the delta that is formed by the two vectors, that is OPQ, delta OPQ, its area was given by half. Anyways, since the OPQR is a parallelogram, so the delta formed by one of its diagonal and the two sides will be half the area of the parallelogram, right? So it will be half of r cross delta r. Okay, and let's call this vector area. Please remember this is a vector, so this will be a vector area. Let's call this vector area delta A. So what is this vector area delta A? This area swept by the radius vector in time delta t. the area, the triangle that will be formed by the position vector when it moves from initial position to the final position, that is known as the area vector, right? So delta A vector will be equal to this, okay, or we can say delta A vector will be equal to, we can substitute the value of delta R as this, so we can say half R cross V delta T. Okay, or we can say this is equal to half R cross V can be written by P by M. Delta T being a scalar, we have taken it outside the cross product. Now what is P by M? See, we know that momentum P, linear momentum, is given by M into V. So V will be given by momentum vector, linear momentum into or divided by mass. Or we can say that delta A vector divided by delta T vector, we have cross multiplying, will be equal to, M being a scalar can be taken out, so will be equal to 1 by 2M into R cross P. Now from a previous video, we already know that R cross P is equal to the angular momentum, right? So we can substitute the value and we get L half L by M. Okay, or we can rewrite this equation as for angular momentum, L must be equal to 2M delta A by delta T. Now what's delta A by delta T? See, we already said that delta A is the area that is swept out by the vector, by the position vector in time delta T, right? So this will be our vector delta A, or sorry, vector, or the direction of vector A or delta A, right? So what we mean by delta A by delta T is that it is the rate at which area is swept out by the position vector of the particle which is rotating about the given axis, that is about the z axis. So delta A by delta T is equivalent to certain type of velocity, and this velocity is known as area, rate at which area is swept out, so it is known as areal velocity. Now this expression L equal to 2M delta A by delta T is a very important expression, and it will come in handy, very much handy in our discussion of planetary motion, particularly Kepler's laws of planetary motion, where we will make use of this relationship between areal velocity and angular momentum. Okay, that will be for the chapter of gravitation. Now let us move on to equilibrium of rigid body. Now what we mean by equilibrium of rigid body is that a rigid body is said to be in equilibrium if it is in translational as well as rotational equilibrium. What we mean by that? See, if the rigid body is not changing its translational motion, that is its velocity is neither increasing nor decreasing or not changing, then we say that it is in translational equilibrium. However, a rigid body which is at translational equilibrium, that is it is not transferring from one point to another, might still be having rotational motion or rotational acceleration. For example, if I take this pen and keep on moving it about its axis, it is not changing its position from one point to another, right? Its position with respect to time remains same. Still it is having a rotational motion, or it might be accelerated in the rotational way. So for a rigid body whose size and shape is important to us, to be in equilibrium, it has to be translational as well as rotational equilibrium. Now what is the condition for translational equilibrium? We know that net force that is acting on it net external force must be equal to 0. So there can be number of forces acting on it. However, if their sum total becomes 0, then the body will not accelerate, or it will have a translational equilibrium. Similarly, if tau external, sum of tau external is 0, that is summation of Ri cross Fi, which is external F, of course, is equal to 0. So if the net torque acting on a rigid body is 0, then the rigid body will be in equilibrium or rotational equilibrium. In other words, if it were rotating at a particular angular velocity, it will keep on rotating with the same angular velocity. If it was not rotating, it will not rotate. It will not change its angular velocity at all. Now, F exterior, sum of F exterior is 0 means that all its components, that is Fx, must be equal to 0, must be equal to summation of Fy, must be equal to summation of Fz. Okay. Again, in case of rigid body, if you remember my first chapter of a system of particles, where we discussed the first video on system of particles, where we discussed about center of mass, we had said that this F exterior, or net force that is exerted on a rigid body from outside, will, if m is the mass of the body and Cm is the center of mass of the body, then net force will be equal to m into ACM. If you haven't seen that video, you may please refer to that. The link will be given in the description below. You can find how we had arrived at this particular expression. Okay. Again, ACM will be dVCM, velocity of center of mass, divided by dt, right? Which means if F exterior is 0, external force is 0, then VCM must be equal to constant. It should not change with time. Now, if VCM is constant, we can have two things. One is VCM is not equal to 0, and the other one is VCM is equal to 0. If VCM is not equal to 0, we call this dynamic equilibrium. That is to say, the body is moving. It will have kinetic energy and all, but the body's velocity is not going to change. It will remain constant or remain the same. So, even if the body is moving, it is said to be in translational equilibrium because of the fact that it's not accelerating at all in any ways. And VCM equal to 0 means it is static equilibrium. Okay. So a rigid body in equilibrium can be in translational, has to be in translational as well as rotational equilibrium. Translational equilibrium can be two types. One is dynamic, where the rigid body as a whole is moving but it's not accelerating at all, or otherwise it can be at a static equilibrium where it is stationary. Similarly, rotational equilibrium also, the body, if angular velocity is constant, it is in a dynamic equilibrium, and if it is angular velocity is 0, it's not rotating at all, then it will be at a static equilibrium. Moment of inertia. What we mean by moment of inertia? What is moment of inertia? See, as of now, what we have discussed about is that when a rigid body rotates, in case of rotational motion, there is a counterpart for force. The cause of rotational motion is known as torque, right? Which is the counterpart for force in translational motion. Similarly, we have angular momentum, which is counterpart of linear momentum for rotational motion. Similarly, if a torque is applied to a rigid body, the rigid body will, of course, because of its inertia, tend to oppose any change in its state of rotational equilibrium. So the resistance that is offered by a rigid body to any change of its state of rotational equilibrium, that is, whether it were stationary, it will tend to be stationary in rotational terms, and if it were rotating about certain axis with certain angular velocity, it will tend to keep on moving, rotating about the same axis with the same angular velocity. That particular resistance or inertia against any change or any applied torque which tends to change the state of rotational equilibrium, is known as moment of inertia. So moment of inertia is basically rotational counterpart of mass. Mass was a measure of inertia for translational motion. Moment of inertia is a measure of inertia for rotational motion. So if we have to define moment of inertia, we would say that it is the property of opposing torque tending to change the state of rest or uniform rotational motion about a given axis. Property of a body that tends to oppose the torque that tends to change its state of rest or uniform rotational motion about a given axis. Mathematically, moment of inertia I is given by, let us say, we have a rigid body and it is moving about the z axis, say. This is x, this is y, this is z. It is moving about the, rotating about the z axis. Okay, so its different point masses are distributed at different points. Let's call at R1 there is a mass M1 which is moving with a velocity V1. Right. At say R2 there is a mass of M2 which is moving with a velocity of V2, and so on, right? So moment of inertia will be, if there are n number of particles, then moment of inertia of the rigid body about the given axis. Please remember, it is very, very important that moment of inertia is always measured about the axis of rotation. If the axis of rotation changes, the moment of inertia of the body will change. We'll come to that in a while. So moment of inertia will be m1 r1 square plus m2 r2 square plus mn rn squared, where these are masses and their respective position vectors, right? We have taken the magnitude because we have taken the square, or we can say this is equal to summation of I equal to 1 to n mi ri squared, which means that dimension of moment of inertia will be dimension of mass multiplied by dimension of distance. So it will be mass 1 and L squared. And its units in SI, the unit will be kg meter square. In CGS, the unit will be gram centimeter square. Now, moment of inertia, since it is dependent on axis of rotation and the mass points and the vector joining the axis of rotation to the mass points, right? The radius vectors or the position vectors of the different mass points of the mass distribution of the rigid body. So mi will depend on moment of inertia, that is mi. Moment of inertia depends on certain points. Number one, of course, the mass of the body. Number two, size and shape of the rigid body. Clearly, a linear body will having the same mass, and a circular disc or a sphere having the same mass will have different moment of inertia about a given axis. Okay. Next is that how mass is distributed. Of mass. How the masses of the particle or of the rigid body are distributed about the axis of rotation. The moment of inertia will be dependent on it. So if it were the same rigid body rotating about the z-axis or rotating about the y-axis or rotating about the x-axis, we have different moments of inertia. Important to note that. And finally, might have different moments of inertia, not necessary, but might have. And last is that, of course, it depends on the position and orientation of the axis with respect to the body. So if the body is along x-axis, whether it's along y-axis, whether it is in between x and y-axis, based on that the moment of inertia will change. So these are the four important factors on which moment of inertia depends, which means that in case of translational motion, mass, which was a measure of inertia, was a constant, right? It didn't vary. However, in case of rotational motion of rigid body, moment of inertia, which is again a measure of inertia of the body against change of state of motion. But in this case, moment of inertia will not be a constant. It will be dependent on these factors. Having the same mass will not mean that it will have the bodies will have the same moment of inertia about the given axis. We will come to that in a while when we discuss or try to find the moments of inertia of different bodies about different axes. That we will do in a couple of videos time. But for now, let's continue from this particular point that moment of inertia is given by I equal to m summation of I is equal to 1 to n mi ri square. Okay, now let's come to this particular diagram or this particular rigid body. What we have seen is that the different mass points have different positions and so different velocities with linear velocities components, right? So when it is making a rotational motion, there will be kinetic energy of rotation. Kinetic energy of rotation of the body will be simply half m1 v1 square, where v1 is the velocity of the first mass, this one, plus half m2 v2 square, where v2 is the velocity of second mass, and so on and so forth, right? So we will say till half m1 n r n square. However, this rotational motion about the axis will have certain angular velocity, right? So r1 into v1 will give us omega, r2 into v2 will give us omega, and so on and so forth, right? This is not r, this is v. So sorry. So what we will have, r1 into omega will give us v1, right? r2 into omega will give us v2, and so on and so forth. Omega will be constant for the rigid body, right? It is the angle subtended by different mass particles at the center or at the axis will be the same for different masses, which we have already discussed in our discussion in the previous videos. You may please refer to them in my playlist, which is the link to which will be given in the description below. So what we will have is that half m1 v1 square can be written as half m1 r1 omega square whole square plus half m2 r2 omega whole square, and till we have half mn rn omega whole square. So what we can do is that we can take the omega common. So half omega common, half we have m1 r1 square plus m2 r2 square plus mn rn squared into omega. However, this term in the bracket is equivalent to this, or that is the moment of inertia of the body. So we can say that k rotational is equal to half I omega square. An important relationship. Kinetic energy of rotation is given by half I omega square, as kinetic energy of translational motion was given by half mv square. Right. Now, if this is so, then we can also rewrite as for omega equal to 1. Rearrange this equation. If you substitute omega equal to 1, k will be half I, or we can say that I equal to 2k rotational. Right. So what we get is that moment of inertia is numerically equal to twice the kinetic energy of a rigid body which is rotating about a given axis with a unit angular velocity. So for unit angular velocity, when angular velocity is 1 radian per second, moment of inertia of the body will be equal to, numerically equal to twice the kinetic energy of rotation of the body. This is important to remember. Both the equations are very, very important. We'll find their use in coming problems that we'll discuss in a couple of videos time. Okay.